Hi, everyone. My name is Tom Shane, and I'm here from MIT Sloan's research papers team. And I'm here to introduce Chris and his colleague, Sergio. And they're going to be talking to us today about their paper, A Switching Dynamic Generalized Linear Model to Detect Abnormal Performances in Major League Baseball. So we'll have about a 20-minute presentation, and then we'll have about 5 minutes at the end for Q&A. So with that, I'll turn it over to Chris.
Thank you very much. Thank you. Thank you, everyone, for being here. This is the work I've been doing for the last few years with a colleague, Sergio Takdar, at Duke University, and we're trying to identify abnormal performers in Major League Baseball. So before I begin, I should say a few words about the limits of our method. We are trying to identify season-level and player-level anomalies. What we are not able to do is make any statements about what's causing those anomalies. So it's a tricky balance, but we're not assigning any causality to these abnormal performances. The story begins with a simple figure. What I presented here are the player-level home run distribution by season from 1950 to 2013. So the top blue line represents the 95th percentile in that distribution, and the bottom red line represents the 25th percentile. The black vertical line is 1990. So see, after 1990, there's an across-the-board shift in home run totals at the player level. So this is an era of great home run hitters, very prolific home run hitters. There's Mark McGwire and Sammy Sosa. There's Barry Bonds. And at the time, we think this is just a golden age of home run production. So the question we want to answer is it possible in near real time to identify that something else is going on? There's some player-level anomaly that's going on. So the data that we have is at the player level for a sample of players from 1990 to 2013. This is an example from Alex Rodriguez. What I've shown here is his at-bat total plotted across his career. And we're going to layer on top of this his home run count. So over the course of their career, we start to get a thought about his home run rate. And it gets us to the idea of this statistical experiment that would be sort of Alex Rodriguez hits Y home runs out of N attempts. So how productive is he in the chances that he's given, which would be a binomial experiment. Except that we don't just have binomially distributed data, we have time-indexed binomially distributed data. So we have collections of binomial time series. And we don't just have it for one player, but we have it for the entire collection of Major League Baseball players post-1990. And so we have this binomial setup. And the whole story of the presentation is really told on the next two slides. So what I've plotted here are the player level, an example of a player level home run probability. So this should be interpreted as player X hits home runs with a probability of whatever percent, 0.05 at each age of his career. So see there's a peak around 30 here, and it diminishes at each side of the age spectrum. But sometimes what we observe are trajectories like this, where there's really sharp deviations from this age trajectory. And so maybe this player has a few stunning breakout seasons in his mid-20s before returning to a more typical age trajectory. Or in other cases, there could be a player who just continues to improve in his ability to hit home runs. So this would be his probability of hitting a home run in a single at-bat just continues to increase with age. And what we're trying to do is to decompose these age trajectories or these probability curves into two different components. A normal component, which would be a component that's consistent with a typical aging pattern, and an abnormal component, which would be the residual or the sharp deviation from that age pattern. The mechanism that we use to achieve this is with a switching ability class model. So an ability class would be a cluster of players that hit home runs with the same probability. So there's 10 different ability classes presented here, ordered from the bottom to the top. So the lowest ability class might be a AAA call-up who's making his major league debut, and the top ability class might be a Hall of Famer. So this blue curve would be an example of perhaps it's a defensive specialist who has a good long career, but never really a home run hitter. And so he stays in the second ability class his entire career. Now note that just because he stays in the same ability class, it doesn't mean that his home run probability is static. It's a dynamic probability across age. So here would be a second age trajectory. Perhaps this player starts in a very low probability class, but then quickly ascends, hits his peak as a near all-star. Perhaps he gets injured for a year before rebounding. Yet a third one where the player gradually climbs, and so they're switching between these different ability classes, plateaus, and then rapidly diminishes in his 30s. But sometimes you observe trajectories like this, where there's a player who's following one pattern and then sharply deviates from this trajectory. And so what we're trying to do is think about the counterfactual. What would have happened if that player had stayed on his current trajectory? And so it gets us to this question of isolating contributions from both the individual ability classes and what we call an abnormal performance. So some of these Greek letters don't look quite right up here, but that's, we'll roll with it. So we have the need to estimate four things as statisticians. So we want to estimate the ability class levels, or the heights of these gray lines that change with time. We need to identify the ability class membership. So for each player in each season, we need to estimate which class does each player belong to. We also need to identify whether a deviation from these aging patterns has occurred. So is that a abnormal performance or not? And lastly, we need to estimate the increase in performance that a player might get if he's designated as abnormal. So on the previous slide, we talked about home run probabilities. So let's think about how these might translate to home run counts. So the example that we have on the left figure, so this would be home runs by ability class. So this is that we're working in a Bayesian statistical paradigm, so we're allowed to incorporate our prior beliefs. And so this is what we've done here. These are prior distributions for home run totals in ability class. As an example, a player in the 15th or highest ability class, it's expected that he'll hit 50 home runs. Now, it's because of the sampling variability in the binomial distribution, it's quite possible that he'll hit up to 65, 70 home runs. And now on the right-hand side, we've increased this performance by this abnormal shift. So for the same player in the same 15th ability class, instead of hitting 50 home runs now as an expectation, he may hit 70 or 75 with a right tail out to, say, near 100. So what we're trying to do is, without any abnormal performance, we're trying to model home run counts that are quite high. So in the left figure, you see that home run counts get to historically high levels, and that's without any abnormal performance shift. So what we don't want is to automatically flag all high home run counts as being abnormal. That would be a failure of our method. And so by placing prior distributions as we have, we preclude that. So the whole model is graphically summarized here. What we have at the top row of nodes, these are the observed quantities. These are the observed home run counts. The arrows represent a temporal dependence, so we have home run counts across time. At the next two levels, the eta and the theta, these are what are called the log odds, or the log probability, the log of the odds of hitting a home run. The bottom two rows are the ability class membership, so which ability class is each player in at each time. And then the last row is the binary indicator variable for whether a player's performance is normal or abnormal. And so these are the things that we need to estimate for each player, except for y. That's what we're given. And the way that we'll do that, again, is with a Bayesian approach. So when we combine all of these different elements, this is the prior belief. This is our prior distribution for home run probabilities across age. So the black line is our expected our expected home run probability for a player who sometimes switches between normal and abnormal. The red line is for a player who is always designated as abnormal. And so in our Markov switching model, so I actually forgot to mention that on the previous slide, for ability class and abnormal performance transitions, we use a Markovian evolution. And so that means that the probability of going to a class tomorrow depends only on my current class today. So that's what a Markov transition process would be. And so the way that we model this is that players younger than 28 years old are more likely to increase in ability class than they are to decrease in ability class. We choose 28 to be consistent with work by Ray Fair, who's an economist at Yale University. He studied age curves and found 28 to be the peak age for Major League Baseball players. We assume a 4-year prime, so from 29 to 32, we say transitions in ability classes are symmetric. They have an equal probability of increasing or decreasing in ability class. And then from 33 onward, we think it's more likely that a player will step down in an ability class than it is that he will increase ability. So note that there's a significant difference between the red line and the black line. So in the abnormal performance indicator as 1, the home run rate jumps quite a bit. And lastly, these dashed lines represent the 95% prior credible intervals, with the bottom end of our distribution going from 9 home runs in 500 at-bats to the top end being about 55 home runs in 500 at-bats. So everything we've discussed thus far has been our model and motivation and our prior beliefs about the distributions. we're going to update those prior beliefs with data to generate our results. And so we generate our results with a custom Markov chain Monte Carlo algorithm that we've developed. What I'm presenting here on the left are the probabilities of hitting a home run for a player in each one of these ability classes. So there are 15 ability classes, and we've plotted against age. And so when we previously discussed ability classes with these dashed gray lines, we sort of hypothesized that there might be this effect where players peak near 30 and then diminish at each side. What we're actually finding is the opposite in the results, and we think this is due to selection bias in our sample. So as an example of selection bias, Ken Griffey Jr. enters Major League Baseball at 19 years old, and he retires at 40. So he's in this sample the entire time. Whereas a more grit and grind type player like Trot Nixon, who played for the Red Sox, enters at the age of 24 and then retires at 34. So we have this effect where there's only elite players at the youngest ages and at the oldest ages, and as a result, that sort of pulls up the probabilities at those ages. What I'm presenting on the right is the computed increase in probability that a player will get for being designated by our model as abnormal. So as an example, if we take a baseline player who hits a home run with a probability of 0.05, the increase that he will get when he's 37 years old is 0.037. So he'll go from a 5% home run hitter to an 8.7% home run hitter, which translates to an increase of about 18 home runs and 500 at-bats. Now, the main takeaway from this figure on the right is that older players tend to benefit more from our abnormal designation than do younger players. The main advantage of our model is that we're able to generate player-level inferences. And so the next few slides will discuss a few individual players. What I presented here on the left is the posterior distribution of Derek Jeter's ability class. So these are which class does Jeter belong to at which year, and the dashed gray lines represent the 95% posterior credible interval. That's our uncertainty about his ability class. So see that Jeter follows this sort of typical aging pattern where he increases in performance, then plateaus, then decreases in the later stages of his career. The middle figure is for the probability of an abnormal performance. So that's the probability that Jeter's performance meaningfully deviates from a typical aging pattern. We've presented 3 different lines here. So one of the challenges as a modeler is that you have to specify how many different ability classes there are, how many different clusters of players there are. And so we want to consider the sensitivity in our analysis to that choice. So we present 3 different choices, one for a baseline of 15 different classes, and then 13 and 17 as well. So notice that Jeter was never a prolific home run hitter. That wasn't a huge part of his game. But we capture that nicely here. So on the right-hand side of this figure, the third figure on the slide, is the posterior probability of Jeter hitting a home run in a single at-bat across the trajectory of his career, across each age. So let's change the story to Mark McGwire, who's a somewhat of a different case. So McGwire was an elite home run hitter across his entire career, and that's evidenced by the figure all the way to the left, which shows he's a member of the highest ability class. We find that starting in 1992, his performances start to look a bit abnormal. So and that's represented by the increase in the probability of an abnormal performance from, say, like 0.25 or 0.4 to approximately 0.9. And so McGwire is traded from Oakland to St. Louis in 1997, and then, of course, he hits his 70 home runs in 1998. So this is somewhat of a different story. Now, all the way to the right, we've presented the probability of him hitting a home run in a single at-bat across his career. And note that it continues to increase. So it seems like time does not catch up with him as a player, which we find to be a bit of an unusual aging pattern. These are the results for Alex Rodriguez. So again, Rodriguez enters Major League Baseball, I think at 18 years old, one of the youngest players ever. And he has a spectacular career. He is an elite ability player almost from the beginning of his career. And let's focus in on the middle figure. So Rodriguez joins the Texas Rangers in 2001, which corresponds to roughly the same time that our abnormal performance indicator kicks up. And then it remains high for the next few seasons. So one of the things that we wanted to do, which we discussed with the rainbow plot, my wife calls it the rainbow plot, that's the prior distribution of home run counts. We discussed how we did not want all high home run counts to be flagged as abnormal. So in 2007, Alex Rodriguez hits 54 home runs, and our method does not find that to be particularly unusual given his elite status and the age of his career. So all of these inferences are conditional on both the player's ability class, age of career, and the ability relative to his peers. So we're trying to generate context for home run totals to interpretate them in a more complete way. On the right-hand side of this figure, you see his probability of hitting a home run and an at-bat, and it has this sort of two-hump feature where it increases, then drops down and increases again. And lastly, these are the results for Barry Bonds. So Bonds, again, is an elite performer across his entire career. And all of these players are the top of their craft, right? They're all-stars, they're Hall of Famers, they're elite players. In the middle figure, we find there's two separate stretches at which Bonds' abnormal performance probability increases. So the first is in 1993 when Bonds goes from the Pittsburgh Pirates to the San Francisco Giants. So he starts 93 with the Giants. That's his first year. The second year in that stretch is 1994, which is the strike-shortened season, where we see an across-the-board increase league-wide in home run counts. Now, the second stretch of abnormal performance begins in about 1999, so that's when Bonds commences really a tremendous run through the big leagues with home run counts, and culminates with his 73 home run season in 2001. Just like with McGwire, we find that Bonds' probability of hitting a home run continues to increase with age. And again, there's two different spikes. So when you take these two figures together, the middle figure and the right figure, the bumps in the probability, the posterior probability for hitting a home run, really correspond to the spikes in abnormal performance in the middle figure. So this is the last figure that I'll show. It's the proportion of the population that's flagged as abnormal by age. So we generate the previous figures for all players in our sample. That's all players in Major League Baseball post-1990 that are position players. And we find that abnormal performance tends to occur more frequently in players at the later ages of their careers. And so at 40 years old, we find roughly 12% of players are designated as abnormal by our method. And the dashed, the shaded blue interval is the 95% posterior credible interval of our estimate. So to summarize, we've developed a data-driven and systematic approach to identify player-level anomalies in MLB. The question is, who cares, right? So why does this matter? So it's possible with this method to do within-season monitoring. So you don't have to just look past, we can look forward. So I'm much more excited about applying this to forward-going concerns than doing a retrospective analysis. So we can think about updating our inferences in the first month of the season, in April, and then updating them again in May, and June, and July, to generate a near online interpretation and inference about player-level anomalies. We can also think about different modeling angles. So in this paper, we focused on abnormal increases in performance. We could also think about abnormal decreases in performance. So sometimes players are injured and either don't report them or they go misdiagnosed or not diagnosed at all. And so you could look at player-level data when there's an abnormal decrease in performance and think about when that player might be playing through injury. You could also use this to evaluate training programs and a host of other things. And lastly, we can think about bringing this to other sports. So in this case, we've generated a model for binomially distributed data, but it doesn't have to be binomially distributed. It could be continuous or really any type of performance data. And so we think that any sport with a uniform performance metric or metrics across all athletes will be a good candidate for this. So it could be applied to track and field, swimming, cycling, et cetera. So what we've tried to do is generate a complete modeling platform to think about player-level abnormalities in a more complete way. So with that, I'll stop and take your questions. Thank you very much for your time. I hope you enjoy the rest of the trip to stay in Boston, and thank you again.
Hey there. I was just wondering if you ever restricted your sample to players that haven't been linked to steroids and see what the results look like.
So it's not that I've restricted my sample in any way. I'm just presenting results for these 4 players. So I have results for every player. The whole sample includes all, so whatever 1,500 players that have played since 1990. So it's not that I'm just focusing in on these players. These are results for 4 different players.
I meant the opposite. If you took those guys out that tested that have been linked and see how the model changes when you have those guys.
So I have not conducted that analysis. It's an interesting question, but I haven't looked at it.
Hey there. So question about the classes that you generated. Did you generate those analytically by some clustering method, or was that kind of handpicked?
No, it's the first. It's analytically. So we apply clustering. So our method is this clustering algorithm. So what we want to find online are these different sort of clusters of players, and that's what we learn. Okay. So we don't just arbitrarily assign, by hand assign players to different classes. We learn what those classes are.
Gotcha. And so how did you determine K here? Just curious.
So
like the number of clusters.
So the way that we did it was by simulating data from different choices and then seeing what looked reasonable, right? So you generate different home run totals, different trajectories, different absolute performance metrics, and say this looks reasonable, this looks too high, this looks too low. I don't believe that there's 3 classes. I don't believe that there's 1,500, right? I think it's some small number. You want to have it be fairly parsimonious so that you effectively share information across these different sets of players. But it's a good question, and there's no right or wrong answer for how you pick that. You just want to acknowledge that there's uncertainty there.
Thank you.
Do you think that there's any possibility that this model could be used to maybe, instigate drug tests for players that are, I know you use McGwire, A-Rod, Barry Bonds, all players that have either admitted to or been linked with steroids. Do you think that this model could be used to get players with abnormal performances to, have steroid drug tests?
So I think that I think you could use it as a monitoring tool. I'm not a lawyer, I'm not a league executive, and so I think a players association would probably not want a statistical method determining drug tests. But I think it's part of the tool, right? It's a tool in the tool belt for thinking about player level and system-wide anomalies. And so I guess that's a question for somebody else and not for me. I think it's a good idea, and that's one thing that I'm excited about thinking about. So thanks for the question.
Hey, how are you? Over in this direction.
Got it.
So you alluded at the beginning of your presentation to plugging and chugging with other variables, and I think that's really interesting. I think with home run, it kind of lends itself to abnormal performance. But are there other ideas of sports statistics in your mind that you think this model would be particularly useful for? And maybe have you played those kind of things out in your own mind of what other variables would work here?
So I think, good question. So I think one of the things that first came to my mind was race times in, say, like swimming or cycling or track and field. So, if you see a player jump from a runner jump from an 11-second, 100-meter dash to a 10.2, I don't know, is that a big increase or decrease? You'd have to look at the context of all runners in the sample and evaluate where they are in their careers. But that was something that came to my mind.
Do you think it would be easy to do?
I don't think it would be. It's not that hard to do. So it would take time. It's not, a 5-minute analysis, but it's not a year-long analysis either.
So I think we have time for just one more question.
Hey, love the work. The examples you gave showed a lot of players with sustained periods of abnormality. Did you see many players with really peaky sort of trends in that regard?
Good question. So one of the things that I did see, I focused on players that revealed different interesting elements of the model. So, McGwire had this really high sustained period. Rodriguez had this sort of bump and then came back down. And then Bonds had these 2 separate stretches. one of the things that we did find was that abnormal performance doesn't have to be for a player who hits 50 home runs. It could be for a player who goes his entire career hitting, say, 1 to 5 home runs, and then at age 36, all of a sudden hits 10 home runs. So we see examples of that in the data. And so there's some interesting phenomena like that that I think need to be more fully explored. And we don't have enough time to or space on these slides to include all these different examples, but it's a great question.
Well, thank you very much.
Thanks, guys.